So in this case, I want us to check how to simplify our complex numbers, which is the part of our J notation, as we are going to be using in our industrial electronics. Yeah, remember, we have got this in our mathematics too, but it is important that from that mathematical concept that you are used to, how are you going to relate in terms of the calculations under the subject that we are doing of our industrial electronics? So in this case, the complex numbers, as we do understand from our mathematics, we've got the two formats that we can actually present our complex numbers. We can present them in the rectangular form. We have got what we refer to as the rectangular form and the polar form. So in this case, we are talking of the presentations. A number that is presented in rectangular form or can be presented in a polar form. These are presentations where in this case, maybe you are presenting Z in the form of A plus or minus JB like this. This is the rectangular format where we have got A representing the real term. That is the real number or the real term. And B is the part of the imaginary term. So there we have got the imaginary term. So what is important is that the real term representing of a term that we do not have, that in this case, we do not have this J. We do not have this. The J is affecting the imaginary term or the imaginary number. And your polar form, remember that this Z can be given as R angle of theta like this. Where now we have the resultant. And this angle theta being the argument. So meaning to say, in our simplifications, as we can see, we've got two formats. We need to understand the simplification of the rectangular form and also the polar form, because each part is important on its own. You are going to see where the rectangular form is important to use, where the polar form is also important to use. So before that, can we convert from one form to another? Is it possible that we can convert from this format to this format, which is the polar form, and vice versa? Yes, that is very, very possible. So that is what we're going to have in that case. So we're going to have converting from rectangular. Let's start from rectangular form to polar form. From rectangular form, that's to polar form. To polar form. Remember what we had in a rectangular form. We are presenting something of this nature. Z is equal to A plus or minus JB. So we want it to be written in polar form, where Z now is going to be written as R theta like that. Okay. So the question is, how is that possible? We are supposed to apply our mathematical calculation, this and that, but because of the issue of calculations, time, this and that, you are no longer going to use those conversions that you were having in your mathematics, where you've got this is your A and this is your B. Then you can have your R in that case, where you can calculate the theta, the R from the square root of A squared plus B squared, the theta being taken from arctan, opposite over adjacent, which is B over A. This is what you're supposed to have, and relate the angle. How is it presented? But this time, you are going to be converting all this using the calculator. Using the calculator. Using the calculator, sorry for that. So I want us to see, how can we use the calculator to convert from a rectangular to a polar form? So this is what we have. I'm gonna also, as I'm presenting the steps, I'm gonna try to write them down. So you need a calculator. As I said, you're gonna be having these conversions on our calculator this time. We're not gonna have the our mathematics concept now. All right, so this is it, guys. On our calculator, let me try share this part and see. You have got this button. If you check here on this plus here, on this plus on top there, it's written pol on top there. That is the polar form. This is a conversion to polar form. On the negative there, if you check here, there's written rec, RCE. This is for conversion to the rectangular form. So once you see this pol, it's saying you're converting to polar form. Once you see the rec, it means you are converting to rectangular form. You are converting to. You are converting to polar form. You are converting to rectangular form. So meaning to say, as you need to convert to what? To polar form. So we are going to concentrate where it's written, all this one, on the positive there, on this positive. So how do I access this? Okay. Let's take an example. Just like I said, I'm going to show you the steps as we are moving on. I'm just going to be showing you the steps. So let's just take for an example. Convert. Let's say we want to convert a certain complex number, which is given as 4 plus J3. Okay, which is given as 4 plus J3, like this. This is in rectangular form. So we want to convert to polar form. Okay, so this is it, guys, on your calculator. So you're gonna use the that part of the pole, which is here on the plus. So how do we access this? It's going to be shift. As you can see, the color there, it corresponds the color that is on shift. So it's gonna be shift. You press the plus. Okay. So as you can see, it's giving us pole, meaning to say we are converting to polar form. So how are we going to convert? You are going to insert these values that are in rectangular form, these ones, the 4 and the 3, taking the sign of the 3, which is a positive. So this is how you insert the values. So it's going to be 4. To insert 3, which is a positive, it's going to be, you use this comma here on this bracket. At the end bracket, there's a comma there on top. So it's shift, you press that. To separate the values, you do not use this one, the dot, this one. You use this one on a bracket. So it's shift, you press the end part of a bracket, this one, the closing part of a bracket. So you now press the 3. It's a positive, just write 3 as it is, close the bracket. By writing is equal to, you are obtaining the answer that is in polar form. So let's get back now to our format so that we do understand how the answer is going to be given. Remember, we said in polar form, our answer is going to be written in the form of r angle of theta, like this. Okay, so you're going to notice that the calculator is going to give you the value of r and also the value of theta. You take those values as they are. Okay, let's see what you're obtaining. So it means 4 plus J3, this one is going to be the same as on our calculator. We can see the value of r in this case. All right, let me see here. We check. R is equal to what? To 5. So that is our r there is 5. Then the angle theta. Okay, if we check here, our angle is given as what? Theta. 36.89 and so forth. You can even round off to 3 decimal place, then 9 is going to affect this into a 7. So that's 36,870. Okay, so it's going to be 36,870, which is just comma 87. We have converted to polar form. So as you can see, the calculator is simply straightforward. So as you saw that you need to, need this, it's going to be shift. Then in order for us to access this pole that we are given there, this one, this pole that is given there, you're going to press the plus button. And it will write pole like this. It opens a bracket for you. You insert the values separated by a comma. You insert another value. Okay. And like I said, guys, you do not use that dot on your calculator. Use the other one that you have to use the shift to access that. This one to access this. It's shift close bracket, that part of the close bracket, closed part of the bracket. Okay. Close bracket. And then you close this part of the bracket that you inserted, then it's equal to. So with this, you can convert anything, whether there is a negative or not. Okay, let's try this one. We want to convert, let us just have a negative. Let's say we are given 5 minus J2 as a negative there. So how am I going to access that? Okay, so as you can see, we need R and the angle theta. Okay, so let's have our calculator. So this is what we're going to have on our calculator here. Gonna have, like I said, you need to convert to what? Polar form. So it's shift plus, where there's a polar form, plus. Then you insert the value, the first one, 5 as it is. To access this number, it's minus 2. Take note, it's minus 2. So it is going to be what? Shift close bracket. So shift close bracket, you access now, you can press the minus 2, this one, the sign, minus 2. Then close everything. This is equal to what? It gives you the R and the theta. So R is what? To 3 decimal place, 5,385. All right, so it's going to be 5,385. Then the angle theta, you check here, the theta, that is negative 21. Okay, let's move on again. Negative 21.801, 3 decimal places. Okay, that's negative 21,801 degrees. So as you can see, you take that answer as it is converted for you. It is converted straight. Meaning to say, we can also convert. So this one, we're converting from rectangular to polar form. Okay, let's just diffuse this one. Then let us convert now to rectangular form. Okay, so you're gonna have to convert. That's converting. We are now moving from this polar form back to the rectangular form. So it's from polar form to rectangular form. Okay, so remember your polar form, R angle of theta, rectangular form. So this is what I need you to understand now, because as I indicated before, I wrote this as A plus or minus JB like this. Okay, this is a presentation that we are actually used to in our mathematical calculation or presentations. But the calculator is not going to give us in the way that we expect. There we are exactly given R. It was actually writing for you R and that theta. It was giving you the theta. This time, the calculator is not going to give us this as A, this as B. It is going to write this as X. Place of A as X, the place of B as Y. So meaning to say, according to the calculator, in rectangular form, we are going to expect this to be written in the form of X plus or minus JY. This is what you're going to expect to be having. So where are they taking this? Remember the Cartesian plan, but we're talking of the Argand diagram, which has got the real axis and the imaginary axis. But they are simply taking to say the real axis, it represents x. The imaginary axis is represented by y, just like the x-axis, y-axis. This is how the calculator is taking it as. So x is simply represent a. So we are still talking of x being what? The real term. And the y representing the part of b, we're simply talking of what? The imaginary term. Imaginary term. So guys, that is how, this is what you just need to understand, the format that you're converting to, and also understand how the calculator presents. But like I said, every format that you're going to need, it's shift to that format. You saw to polar form, you press the pol. This time you need where it is written rec for rectangular form. All right, so this is it. Let us just have an example here. E.g. for an example. Okay, that's what we have there. Convert. Let us just say 5 angle of 30 degrees. Okay, to rectangular form. To rectangular form. So as we can see, guys, this is our polar form of r angle theta. Do not worry. We are not worried about the calculator is going to give us everything. So on our calculator, this is what we are going to have. Okay, let me just have it here. Remember the conversion part. You need to convert to rectangular form. So you press the rec, this one, where it's a negative there. So it's going to be shift. You press the negative this time. So it's shift negative. It opens the bracket for you. Then you insert the values that are presented here, the 5 and the 30 separated. So it's going to be 5. You separate the same thing that we did there. So it's shift close bracket to separate this with 30. So you just write 30 as it is. You close the bracket. The moment you equate this, it gives you the values in a rectangular form. Remember, like I said, the calculator does not understand this A and B. It understands X and Y. So it's going to be X plus or minus JY. So we are given the X, as you can see. We are also given the value of Y. So X to 3 decimal place. Okay, let us just have it here. So it was 5 angle of 30 degrees. So it's going to be equal to X, the real term. Okay, our real term X 4,330 to 3 decimal places. It's just going to be 4,33. So it's going to be plus or a minus. So you have to check the value of Y that you're given. Is it a plus or is it a minus? So the Y that we have is a plus. So we are going to have plus. Y is always with what? A J. That's the imaginary term. So that's J, the value of Y that we got there, which is 2,5. Just like that. So this is how you can simply convert to a rectangular form. We are back to the rectangular form. So the calculator, this is your X, this is your Y. In our normal understanding, this is what? This is our A, this is our B. This is what we understand. So that is what you're going to need in that case. So as we saw, we are now going to need shift to convert. This time, this part, we are going to need shift. Okay. Then you press the part where the rectangular is, and you saw the rectangular is on a negative button. So you press the negative button. The moment you do that, it is going to write rec like this to show you that you're converting to rectangular form, and with an open bracket where you need to insert the value separated with another value that you are given, in this case from what? From these values as they are in that order, 5 and 30 in that order, which is your R in this case, and this is your what? Your theta. So like I said, this comma that you're seeing here, it's always from what? Shift. You go to the button of the close bracket, shift close bracket. Okay, let me just say shift close bracket. That's it. You check where there is a closed bracket there on your calculator. That's it. The moment you equate this, you're now obtaining the value of x and the value of what? The value of y, which represents x, a real term, and y, an imaginary term in rectangular form. All right, let's just try another one. Maybe that can have a negative angle. You can be given a negative angle. Okay. Okay, let's just say this is 1, 2. Want to convert to rectangular form. And you are given 4 angle of minus 60 degrees. Convert this to rectangular form. Okay, so how are we going to convert? Just like what we had previously. So it's going to be shift to rectangular form. Okay, so this is what you're going to have here. So we're going to have shift. We are converting to what? To rectangular form, negative. It opens the bracket where you need to insert the values, the R that you are given in polar form. What is the value of R there? That is 4. You insert that. It's going to be 4. The angle in between, which is separated by this comma there. So it's going to be shift, close bracket. Then minus 6, the angle is having a negative. So it's minus 60. You close that bracket. So this is equal to what? As we can see, we are given the value of x and also the value of y, as we are expecting it to be in rectangular form. So meaning to say our x is what? It's a 2. So we're going to have our x, the real term, which is a 2. The other part is the imaginary term, which always goes with a j. But is it a plus or is it a minus? That is why I wrote plus or minus there. This y that we have is a negative. The y that we have is a negative. So that's minus j. Then we can write the value of y that we have to 3 decimal place. That's 3,464. Okay, that's 3,464. That's it. We have converted to the rectangular form. So we shall see as we are revising this part of our complex numbers in terms of their simplification conversions. As you can see, guys, it's easier. Just need your calculator. We are not going back to our mathematics where you use that z is equal to, now we have got r, the square root of a squared plus b squared, eta is acta. No. We are not in mathematics, guys. So that part you do it when you're in mathematics. So in our simplification, because this subject is not for maths, but it has something that is from our mathematics. That is why we just take that part of our, that is why we neglect the part of the mathematics, like, because we are not under mathematics, guys. All right. So with these complex numbers, you are going to see that they are going to be also useful. Okay, the polar form can be used. Polar form can be used in presenting Phasor diagrams. Wow. Okay, that's another thing to note, that the polar form, okay, sorry for that, the polar form can be used in presenting Phasor diagrams. Okay, we are going to talk about that when it is applications. Now we are now referring to the topic. But you will see that later on, maybe you're talking of the impedance. It is given Z is equal to 4 angle of maybe 30 degrees like this, ohms. And you need to present a Phasor diagram. Remember, your Phasor diagram is having also impedance. Where you want to present that impedance, you can simply indicate the angle of the angle and this number, which is representing our resultant. So the angle here is going to be useful to say, is it positive or negative. Remember, guys, from our mathematics, once we deal with an angle, the sign is important. The sign is important. You are going in this direction, which is the anti-clockwise direction. Anti-clockwise direction. It means you are talking of the positive angles. You are going in this direction, which is the normal direction that we are used to, the way the clock moves. The clockwise direction, the angles are taken as negative. So any angle that is in a negative way, you present it going this way. Any angle in a positive, you present this way. Not forgetting that in between these quadrants, they will be separated by 90 degrees, 90 degrees, 90 degrees from each point. You'll be separated by 90 degrees from each point. So meaning to say, I want to present 4 angle of 30 like this. 30 degrees is a positive, as we can see. So which direction? Positive, anti-clockwise. So you're going to present anti-clockwise from the 0 degrees here, going in the anti-clockwise. But this is before 90 degrees. So you can just assume to say, okay, 30 degrees is somewhere there. Then we present our Z. So this will be 30 degrees, and our Z is equal to what? To 4. We've presented it using the polar form concept. So if it was a negative, we are given minus 30 degrees here, you're going to present it in the other way, negative angles going this side. So meaning to say our diagram was going to be this side. So on the diagram, there is no need for you to write that this angle is minus 30 degrees. No, you just write it as 30 degrees. What is important is the direction that you have taken your angle to. So if it was a negative, we're going to have our Z this side. So that is, we are going to notice that in our presentation later on of this polar form. It will be important. Okay, let us move on to another part which is going to be important in our simplification, working with complex numbers now. As we have seen, as we have seen that there are formats there that can be used to present conversions, and which are also important. But when dealing with complex numbers, when working with complex numbers, we are also ought to understand what is important in terms of simplification. A number which is in rectangular form, or any presentation that is in a rectangular form, and a presentation that is in a polar form. The way that we are going to simplify, or how best do we simplify, it differs with the formats. You are going to see that in a rectangular form, it will be best to say that we are given numbers that are in rectangular form, for you to apply this where we have got addition and subtraction. Whenever you've got something that is in rectangular form, addition and subtraction will be very, very possible to work your questions. I'm saying it is best. If I'm given numbers like this, 3 plus J4 multiply to 5 plus J3 like this, I can multiply these numbers. I can multiply the numbers. But now, because of the simplification that we have, guys, we are not supposed to be like we are back to our mathematics. No. These things can be avoided. For multiplication, even for division, now imagine you are given Z, which is equal to 3 plus J4 over 5 minus J3, and you're supposed to work with the complex conjugate, where you multiply with the 5 plus J3 first, then you convert. No, no, no. These conversions these simplifications can be avoided. You focus with addition and subtraction in polar form. In a rectangular form, where you are given Z1 is equal to A plus JB. And you are given Z2 equal to A, let's say this is C plus JD, like this. If I am to add Z1 plus Z2, guys, it's easier because we are simply considering the real terms on their own. So I can simply add the real terms together. A plus C plus I can simply add the imaginary terms on their own. That is B plus D. You're going to see that in simplification. Same with the minus. If it was a minus, you're going to subtract. So that's why I'm saying it is easier for you to add or subtract in what? In rectangular form. So what is best now for polar form? For polar form, it is going to be best for us to use it whenever there is a multiplication and a division. A division. These two, they will be very best for us to apply the polar form. In terms of simplification, I'm given, let us just say, two numbers that are in polar form. Z1 is equal to, remember, the presentation polar form. It's the R and the theta there. So let's say this is R1 theta 1, and you are given Z2, which is given as R2 angle of theta 2, like this. Okay, guys. For a multiplication of Z1 and Z2, it's going to be very easy because remember from your mathematics, now you can go back to our mathematics laws. You multiply R1 and R2 together. So this is the product. Okay, remember that's R1 times R2. What about the angles theta 1 and theta 2? For a multiplication, the angles you add. So it's theta 1 plus theta 2. Add angles. You add the angles. This is for a multiplication. If it was a division, guys, we're simply going to divide Z1 over Z2 like this. You're going to divide R1 to R2. So it was going to be R1 over R2 like this. What about the angles now? You subtract. So theta 1 minus theta 2. What is on top minus below? So that's going to be theta 1 minus theta 2. So once you can see, because we want to avoid those many calculations. So deal with the multiplication and division, leave that for polar form. Addition, subtraction, leave it for rectangular form. So you will see that when you are dealing with circuits, because we're going to I'll be talking of the RL circuits, this and that, you will see the importance of this. So just a recap. You are given, now the question will be like, okay, let's just say we've got, just going to work with two examples for our simplification. Like I said, it is important for us to multiply in a polar this and that. So we just need examples that we can apply this concept. All right, let us just consider for addition and subtraction. Let's say you're given two complex numbers that we need to simplify that are under addition and subtraction. 4 plus J2, then we are adding this to 3 plus J5. That is, if it is in rectangular form like this, it's going to be easier for us to add. Just going to take 4 plus J3, J2, expand your brackets. This is 3 plus J5 like that. There's nothing that is affecting our brackets there. Okay, so according to this, I'm going to talk of the real terms, the 4 and the plus 3. That is the part of the real terms. The imaginary, that's plus 2 and plus 5, the number and the sign. So you have to consider that. So you're simply going to add 4 plus 3, which is 7. The real terms on their own. The imaginary on their own. So it's plus 2 plus 5. So plus 2 is just 2, plus 5 is just plus 5. So 2 plus 5, that's a 7. So it's going to be plus J7. As you can see, it's easy for us. If it was a minus here, let us just say we've got a minus. What is going to happen? Still the same thing. You have got a minus here. So meaning that this bracket is going to be distributed by a negative 1. We're going to expand by negative 1. So that's 4 plus J2 minus times 3, which is minus 3. Minus times a plus, that's minus J5. This is where we are. So again, we are back to our terms. Okay, the real terms on their own, the 4, the minus 3. The imaginary terms, they have to consider the part of J, but this is plus 2 minus 5. The sign has to be considered there. Okay, so the part of the real terms is 4 minus 3. 4 minus 3, that's 1. 2, that's a positive there. So it's 2. The part of J there, there's a negative there. So it's minus 5. 2 minus 5 is what? It's minus 3. So meaning to say J is going to be affected with a minus. So it's going to be minus J3. So the sign is important in your simplification. So addition, subtraction, with your, simplify as it is in rectangular form. As long you're under multiplication now, you're now given to simplify, maybe it's a product of 3 plus J4 being multiplied to 7, then there we are given minus J3. This is what you're given to simplify. And you can see that the product there. Do not waste your time by expanding all this. It's a multiplication. It is best for you to do it under the polar form. Under polar form. So you're going to see that. All right. So under polar form, how do we multiply? And how do we divide? We saw that we simply have to multiply the resultants. If it is multiplication, add the angles. Division, divide, subtract the angles. For an example, let's say you are to simplify a 10 angle of 30 degrees over 5 angle of 20 degrees. The division. So you simply divide the numbers on their own. The angles on their own. But you have to subtract the angles. So it was going to be 10 over 5. The angle, you subtract this 30 minus 20. So meaning to say this will give us a 2 angle of what? 30 minus 20, which is 10 degrees. So as you can see, it's very, very easy. And after this, we can convert to rectangular form. Whatever format that you're given. Same as the multiplication, just have to multiply, add the angles. So now, let's say we are given 3 angle of negative 90 degrees. And this is multiplying to 4 angle of 20 degrees. It's a multiplication in polar form. So it's R1 times R2, meaning to say 3 times 4. So this is going to give us what? 12. Angle of what? Theta 1 plus theta 2. You add the angles. Theta 1 plus theta 2 minus 90 degrees plus 20 degrees. So this is going to give us 20 angle of minus 70 degrees. So it's easier to simplify. So as we saw previously that we can be given something that is now under a Cartesian form, but it's a product or it's a division. You're given 5 plus J2, and this is multiplying 4 minus J3. Instead of you expanding the brackets, guys, multiplication is best in polar form. So convert this to polar form. Convert this to polar form. Then you can simplify. There's nothing difficult because our calculator is going to do that. Remember how to convert to polar form the way that we did previously. All right, so this is what you're going to have. So let us just quickly see how to deal with this one. You simply convert to polar form. So let's start with the first bracket. So that's shift to polar form, press a plus. First number, 5, separate the shift, close bracket, you press the 2. Okay, so this is equal to what? So in polar form, remember, you expect R and theta. So R is 5,385. So it's going to be 5,385. The angle theta, which move on here, theta is given, that's 21,801. Okay, 21,801. That is the first part that we are having, which is going to multiply this. Let's convert it again to polar form. Okay, so it's shift polar form. Separate the numbers for shift closed bracket. So you're going to press -3. There's a minus there. So it's -3. Okay, let's see what we're going to have. Our R there is 5. So this is going to be 5 angle of theta. So if you check our theta is a negative 36.8968. So this 8 is going to change this into a 10, 9 into a 10. So it gives this one to be a 7. So that's negative 36.87. Okay, negative 36.87. This is what you're going to have. So meaning to say, we are now back to say, once it is in polar form, as we saw that the numbers can be multiplied together. This is what we understand about the polar form now. So meaning to say, you are simply going to multiply the numbers. So this is very important, as you are going to be you are going to be having these steps where you are forced to do all these things. So they're just going to multiply the numbers 5,385 times 5. So this is going to give us as a decimal 26.925. So that's 26.925. The angles, as we saw, we're going to add. So we're supposed to add 21.801 plus minus 36.87. So as you can see, plus and minus is going to give us a negative at the end. So you're supposed to add, even if you simplify like that, just add, no problem. 21.801 like this, then plus, and this one is carrying a negative. So just open a bracket and write as negative 36.87. The calculator is going to simplify for you. So that's negative 15.09. Okay, so this was going to be 26.925. As we saw, our angle is negative 15.069. Negative 15.069 degrees. Okay, sorry for that. So this is our theta in degrees. You've simplified. It was best that we do in polar form, as you can see. You're not going to have all those stages that you have in your mathematics. Sorry for that. Let's see. Sorry for that. See these networks, guys. But anyways, so here, you do not have much simplification to take. So as this is your answer, this one, which is in polar form, it's going to depend with the question. The question maybe wants you to simplify in rectangular form. You can convert to rectangular form. Calculator. Back to the calculator again. So these are the steps that you're going to be having. Conversion from one stage to another. That is best to use. So this is what I want you to just take this in consideration as we are going to be dealing with our industrial electronics class. If you understand this, you're done. Addition, subtraction, rectangular, multiplication, division, leave it for polar form. Okay, so all this part that we have been presenting, the simplifications, the conversions, why is it important in industrial electronics? These formulas, they can be used in a comparison between simple, all right? Okay, let me explain this way. Remember before, you had a simple simplification, actually, a simple simplification of our RLC circuits. We want to see where we're going to apply this. So instead of us working that, we can use the complex notation in simplification. So that is where our complex numbers now, the J notation is playing a role. It can be used in what? In our network, in the circuits that we had. Any given combination, is it for an RLC in parallel? Is it going to be for an RLC in series? So we're going to have, or we need to know the comparisons that can take place between the simple notation that we had and the complex notation that we are going to be having. So this is it, guys. I'm just going to simply have it this way. Maybe we can understand each other. In RLC circuits, we are now talking of the application now of the J notation, the complex numbers. Before, we had a simple notation that we used to have. If we check all the examples that have been doing, they were for just a simple simplification. Then we are going to have the complex now. So let us consider to say you have got an RLC circuit. There is a resistor, inductor. So the resistor is not affected by the J. It is affecting the inductor and the capacitor. Before, you used to calculate your reactance XL as 2 pi FL, and it will just end there. But this time, you're going to see that this reactance is going to be affected now with a J. So for an inductor, it's going to be a positive. So we are going to have our XL as J times the 2 pi FL. This part representing the normal XL that we are used to in a simple notation, but now it's having a J, which can be written in polar form as XL angle of 90 degrees for a purely inductive part, a purely inductive part. Whenever there's a purely inductive part that you're dealing with, it will be at positive 90. Meaning to say, when it is for XC, what is going to happen? 1 over 2 pi FC that we are used to. This time, it is carrying a negative. So it's negative J into 1 over 2 pi FC. So representing the XC, this one, but with a negative now. And this simply tells us that we are going to have this as XC, angle of negative 90 degrees in polar form. Purely capacitive, it will be at negative 90 degrees, which is the theta that you're given. So in the simplifications, it will be important that you understand that there's now the angle used. You were calculating your impedance before, straightforward. The impedance Z is equal to the square root of what? R squared plus the difference that you're going to have. You compare is XL or XC that is bigger than you subtract, then you square it. But this time, you're just going to have our Z as R, as we are seeing that the part of XL is a positive, the part of XC is a negative. So it is going to be plus J XL minus XC to show that XC is carrying a negative always. XL is carrying a positive always. So meaning to say, if we simplify this part here, if you subtract these two, and the answer is a positive, it means your circuit is just more inductive. Remember, there's a capacitor there. So it is just more inductive, mainly inductive. For a negative, it means the circuit that you are given, it is more capacitive. The path that you have taken, that is what it would just say, simply means. So all that part that we had, guys, is it of the voltages? You were just calculating maybe voltage. You just calculate current times resistance. Is it about the resistor? Where this is current across the resistor. Now we're not going to just calculate that. This voltage that you're going to have is going to be from the current that has got a certain angle. And the resistance that is going to have will be having a certain angle. So remember, multiplication based in what? In polar form. So you'll be given the angles that you're going to be using in terms of the simplification. So what I want you to know is that in polar form, in our simplification of the circuits, the part where the capacitor is, that is the most, all these things guys will see that the part where the capacitor is, the plus J. And the part where the inductor is here, inductor, it's a plus J. The part where the capacitor is a minus J. So whatever simplification that you have, you need to calculate XC as usual, your XL as usual. You calculate these as usual. These are the values that you're simply substituting here. Meaning to say, if I am given something like this, let us just quickly present this. So I'm just going to write in terms of reactances. We're going to see that in our simplification later on. Do not worry. I'm going to talk of these examples. Let's say we've got a resistor, an inductor, and a capacitor. But we are given the resistance values, meaning to say we are talking of the reactance. They can give you the reactance of this. Okay, in fact, they are not going to write like this is XL. They will just write here 7 ohms. They will just write here 3 ohms. You're supposed to know what are you given. This is not like we are given millihenries or it's ohms. Is the reactance of the inductor, the reactance of the capacitor. And maybe they'll ask you to calculate total current, whatever that you're given, which is supposed to be taken from the impedance. So you will calculate your impedance from the formula R plus J, the difference null of XL minus XC. So that Z is equal to R in that case, which is 10. Class J, XL is what? The reactance of the inductor, which is 7, minus that of the capacitor, which carries a negative always. They are not going to write it as a negative. It is you who is supposed to know that capacitor is negative. So Z is going to be 10 plus J, 7 minus 3, that's a 4. So as you can see, we've got a positive, meaning to say our circuit is more inductive. Less in terms of what? The reactance of the capacitor, but in terms of the reactance of the inductor, you can see that it's much. So this is what you'll be having now, meaning to say you have got your Z, whatever that you have, and you can even convert this Z to polar form. Remember, we talked about that. Now it's easier to calculate. So when simplifying, as we are going to be having circuits, after this, we are going to be dealing with circuits now, working with circuits, how to work with the J notation. As you are going to be simplifying, it will be best for you to know both formats. Both forms must be known. The rectangular and the polar form must be known. Conversion from one form to another also is supposed to be known. From rectangular to polar and the vice versa. Polar to rectangular form. And to understand that in a polar form, you are going to be mainly using these calculations of a polar form for multiplication and division. For multiplication and division. Limit it only these two in your calculations as we are going to be dealing with our circuits. And the rectangular form, you limit it to what? Addition and subtraction. Anything that has to do with addition and subtraction. Convert whatever. If it is in polar form, convert it to rectangular form. Then you can add or subtract. Then you convert it back to polar form if it is necessary that way. So as we are going to be working with our circuits, I just hope we will be together in our revisions. So do not miss out the revisions. Just make sure you also try to grasp one or two so that we're now dealing with questions, actually examples. You'll be in a mood to, or like you'll be understanding like what exactly are we talking about. Just go through this. Everything is going to be easier to understand till we meet again.